Hello, Pre-Algebra students. Welcome to Chapter 8.8, Systems of Linear Equations. Thus far, we've only been graphing single linear equations. Now we're going to learn to graph and solve systems of linear equations. Let's begin. A system of linear equations, sometimes just called a linear system, consists of two or more linear equations with the same variables. An example would be y equals 2x minus 4 as equation 1. And as equation 2, you might have y equals negative 3x plus 1. A solution of a linear system in two variables is an ordered pair that's the solution of each equation in the system. In other words, it's a point where the two lines meet. A linear system has a solution at each point where the graphs of the equations in the system intersect. Okay? So any point where y equals 2x minus 4 and y equals negative 3x plus 1 would result in the same ordered pair would be considered a solution. Let's work through an example so you can see how this works. Equation 1 and equation 2 have each been graphed in this image. Please excuse the slight curve in the graph. We're going to look at this graph and identify an apparent intersection. And it looks like the two lines cross at point 1, negative 2. Now we want to verify that this is a solution of our system by substituting 1 for x and negative 2 for y in each of our equations. So let's use equation 1 first. We're going to substitute negative 2 for y and 1 for x. And this gives us a solution of negative 2 equals negative 2. Okay, so it works for that equation. Now let's work through equation 2. Y, or negative 2, equals negative 3 times 1 plus 1. Well, that also works. Negative 2 equals 2. So we can safely say that a solution to this system of equations is 1, negative 2. In our first example, we saw that the graphs of two linear equations can have exactly one point of intersection. That related system has exactly one solution. However, it's also possible for a linear system to have no solution at all, or infinitely many solutions. Let's work through an example where we solve a linear system that has no solution. Our equations will be y equals negative 2x plus 1 and y equals negative 2x plus 5. You can probably tell right away that these lines are going to be parallel because they have the same slope. Let me show you the graph to verify that thinking. Here are two functions graphed. We can confirm that the lines are parallel by observing from their equations that they have the same slope, negative 2, but different y-intercepts, 1 and 5. Now, because these lines are parallel, the linear system has no solution. There's no point at which the two lines will cross at a common point. All right, now let's solve a linear system with many solutions. Here are the equations we'll begin with. Equation 1 is 2x minus y equals negative 3. Equation 2 is negative 4x plus 2y equals 6. Our first order of business is to rewrite these equations in slope-intercept form. Equation 1 will become y equals 2x plus 3. And equation 2 will become y equals, 2x plus 3. Hold on a second. These two lines have exactly the same equation. All right, since we can see that the slope and intercept form of both equations is identical, the graphs of the equations are going to be the same line. So the two graphs have infinitely many points of intersection. The system has infinite solutions. Any point on the line y equals 2x plus 3 represents a solution to this pair of equations. Now try this on your own. Solve each of the linear systems by graphing. Give the point of the solution or answer no solution if none exists. Also, if there are infinite solutions, indicate that. Press pause while you work. When you come back, we'll do a little bit more work with systems of linear equations. let's use what we've just learned about linear equations to write and solve a system that will help us compare two plans for high-speed internet service. In Plan 1, you, the customer, will pay $200 for a modem and then $30 per month for your service. In Plan B, you get the modem for free, but you have to pay $40 a month for your service instead. So we want to figure out two things. One, after how many months are the total costs of the plan the same? And B, when is Plan A the better deal for you? Or when is Plan B the better deal for you? So let's begin by writing each plan as an equation in slope-intercept form as a linear system. So Plan A would be y, the total cost, equals 200 plus 30x, with x being the number of months. Plan B would be that y equals 40x, because the modem's free, correct? So here's our system of linear equations. Now let's graph. The best way to graph this system, honestly, is with a graphing calculator. When I see you in class tomorrow, I will show you how to use the graphing calculator app on the iPads. For now, though, what I'll tell you is that we have a point where the lines will meet, which is right around 2,800. So let's go ahead and just plug that in, though, just to show you how that works, that right around 20 months is the magic time frame. So if we have 20 months going here, that's where it's going to equal, let's see, 200 plus 600, it's going to equal about $800. And over here, if y equals 20, then it equals about $800. So this will let us answer our questions, however. The first question was, after how many months are the total costs of the plans the same? And the answer to that is 20 months. At 20 months, the two plans break even with one another. Question B, when is Plan A a better deal? Well, Plan A is a better deal if you are planning to have the service for more than 20 months. Because after that point, you've paid off the modem and your monthly cost is lower. However, if you don't plan to have service for 20 months or more, it's probably a better deal for you to go with Plan B, where you pay the slightly higher monthly cost, but just rent or borrow the modem. All right, sorry for the confusion with not being able to show you the graph here, but I will teach you how to do that with the graphing calculators when I see you tomorrow. Thanks so much for your hard work on this. When I see you tomorrow, we'll also practice together on more linear systems. See you then.